Hello everyone, my name is Alka Foguchiman, and now it's my turn to do my presentation on deep learning technology for noise barrier in encapsulated structure. So here the noise barrier technology is active noise control applied to encapsulated structure, which means aircraft, cars, or trains. In that type of structure, we traditionally use sound absorbing materials. But as you can see in this example of wall attenuation index, the attenuation of noise at low frequency is poor. So that's where active noise control can be a solution to control to reduce the noise at low frequency. So I think you already know that the principle of active noise control, which is emitted noise in phase opposition with the noise that we want to control in order to cancel it. But active noise control can present some problems. So the first one is that the traditional algorithm can present a converging time, which means that the controller needs time in order to understand the disturbance and adapt itself to control it as best as possible. In presence of non-linearities, the control can be not effective. Just to define briefly what is a non-linearities, it's when the relation between the input to a system and the output is not linear. So as you can see in this graphic, the green line is when the relation between the input and the output is linear, whereas for other curves, the system is not linear. And usually in active noise control, these non-linearities can come from the electronical device of our setup, such as loudspeaker or amplifier. In the history of ANC, there was a different algorithm which tried to manage these non-linearities, such as Volterra FXLMS, tangent hyperbolic function FXLMS, leaky FXLMS, or filtered SLMS. But but in presence of strong linearities, the control provided was not effective. That's where deep learning can be a solution, because it is a data-driven approach who allows us to capture or predict the acoustic pressure due to their ability to capture spatial coherence patterns in a related acoustic pressure field, dealing with nonlinearities in the electroacoustic system as well as broadband noise removal, dealing with non-stationary noise, and it gives us the liberty to choose the type of input data to the model, which will be, in our case, signal in time domain, spectrogram, or controller waves. With deep learning, we can use different techniques. We can extract features of the disturbance, which means extract the principal characteristics of the disturbance in order to reproduce it and emit it in phase opposition with it. To do this, we can use convolutional neural networks, so there are different types, or we can do a time domain study by using recurrent neural networks. Here I have listed different type of architecture who can be interesting for active noise control, which are autoencoder, generative adversarial neural network, transformer, or diffusion model. I have two examples of deep learning-based active noise control algorithm. The first one is called DPANC, and here the strategy is to calculate the spectrogram and the spectrogram of the disturbance and split it in real and imaginary parts. So here the objective is to reproduce the noise of the primary pass and emit it in phase opposition. Note that here there is a function that I've told you in order to simulate the non-linearities of the system. And when we check the results, we can see that the control is effective. And at low frequency, if we compare with other traditional active noise control algorithms, the control is more effective. And at higher frequency, we can see that the control is also effective. But of course, in this frequency range, we will use more passive solution. The second one is called denoisenet, and here there are two diagrams. The first one, the difference between both is that the first one, in the first one, there is just the deep learning algorithm, which is here. And whereas in the second one, there is the deep learning algorithm with the estimation of the secondary path deep learning based. And when we check the results, so here the controller is also effective. And in frequency domain, that we can see that at low frequency, when we estimate the secondary path, the control is more effective. So to conclude, so the deep learning can improve the ANC system with its adaptability to noise and acoustic change. Deep learning models can achieve significantly higher effectiveness compared to traditional algorithms. Deep learning enables rapid low latency decision making for real life noise control, and it provides advancement in handling real world noise and environmental changes. So that's all for me, and thanks for your attention.